Welcome to Godot C# Essentials, a complete beginner's guide. This course is designed for anyone who has a basic understanding of programming and wants to learn how to apply those skills to making games. And we're not going to cover every detail of the C# language. There's plenty of tutorials online for that. Instead, we'll focus on how to use C# inside Godot to bring your ideas to life. Along the way, we're going to explore many concepts, including scenes and nodes, the core building blocks of Godot. You'll create a controllable player that responds to input and learn how to quickly prototype levels using CSG nodes. You'll also add interactable objects to your world and build a simple user interface so your player can craft their very first recipe. To get the most out of this course, make sure to clone or download the GitHub repository. And inside, you'll find starter and final projects for many of the lessons. You'll also discover a final sample project called Flyby Cafe that goes a step beyond what we cover here, giving you a chance to peek at how the same techniques can be taken even further. And at the end of most lessons, you're going to find a short challenge. These give you a chance to take what you've just learned and apply it in your own way, helping the skills stick while also giving you the room to be creative. Now, by the end of this course, you'll have a solid foundation for using C# within Godot's workflow, the perfect starting point to bring your own game ideas to life. Let's dive in. Now, before we start building games, we need to set up the development environment. And in this lesson, we'll go through everything that you need to get started with Godot and C#. That means that we're going to install Godot with .NET support, set up Visual Studio Code as the editor, and make sure that C# and the .NET SDKs are installed so that your scripts will run correctly. And then finally, we'll download the course project from GitHub, and this includes all of the starter files and completed projects that you'll need to follow along. So by the end of this lesson, your machine will be ready to go. Okay, let's start by getting Godot installed. First, head over to the official Godot website, and on the downloads page, you're going to see a few different versions. Make sure to grab the one that's labeled .NET, as this version is what is going to include C# support. Once it's downloaded, open the zip file and extract it somewhere that's easy to find. I'm dropping mine into my development folder. And then inside the folder, you're going to see the Godot executable, and that's what we're going to launch in a bit. But for now, let's set up our IDE. To install everything else, we're going to use winget. So open PowerShell and enter the winget command that you see here. Now winget is going to download and install VS Code for you automatically. If you're not familiar, winget is the Windows Package Manager. It's a built-in command line tool that lets you quickly install software without needing to open a browser or click through the installers. Okay, now that that's done, close and reopen PowerShell. And this is going to refresh the environment variables so that we can do the next installation. And let's install the C# DevKit Visual Studio Code extension. This is an extension bundle that sets up all the basics that you're going to need to write and debug C# code. Now, the last thing that you're going to do is install the .NET 8 SDK. Godot 4.5, which is what you just installed, specifically requires .NET 8 to compile your C# scripts. So this part's important. But it's also worth noting that if you're watching this video and a new version of Godot has released, the required .NET version might change. You can always check that on their website. Okay, great. Now let's configure Godot to use VS Code. Double-click on the Godot executable that you extracted earlier and create a new project. Now the settings that you use here are going to persist across editor, or rather projects. So this is a project you can literally call delete and then delete right after. Inside the Godot engine, go to Editor, Editor Settings, and then search for .NET. Click on Editor and set the external tool to be Visual Studio Code. This setting tells Godot to open your script files directly in VS Code. So say you're working on a project and you double-click a script, it knows to open up VS Code directly. We're going to dive deeper into how Godot Project Manager and the editor works more in the next lesson. But for now, this step just connected everything together so that Godot knows where VS Code lives. But we do need to make sure that VS Code knows how to run and debug your project. So the easiest thing at this stage is to right-click on any file within the file hierarchy and click on Open a Terminal. What this is going to do is open a terminal in this file location. And if you type code space period, that is going to open up VS Code at the same location. The next steps that you're going to do are ones that you will need to do for every one of your projects. Now, the nice thing is you don't have to do it manually. You can just literally copy the files that you're about to create over into your next project. But just remember that these files are necessary for every single project. Now, you're going to add 2 configuration files. One is for tasks and one is for launch. So let's start by creating the task file. Press Ctrl-Shift-P and type in task. Pick Create Task from Template and then choose .NET Core. Now replace the text with what you see here. Next, go to the Run and Debug section on the left and click Create a Launch File. Choose C#. Now you need to add the configuration properties, and the big thing that you're going to want to do is replace the program path to where you extracted your Godot files. Now finally, there's one last extension to install, which is the C# Godot Tools extension. On the left side of VS Code, open the Extensions tab and search for Godot. It should be within the top 2, and install the one that is C# Tools for Godot. The last thing that you'll need to do is download the course files from GitHub. You can get the files from the video description below, and once you're on GitHub, you can clone the project or simply download the zip. And with that, your setup is complete. Getting everything installed isn't the most exciting part of game development, but it's necessary. So in the next lesson, we're going to get into the fun stuff and jump into the Godot engine to create your first project. The point of a game engine is to handle the heavy lifting of things like rendering, audio, physics, and input. And by taking care of those systems for you, Godot frees you to focus on the creative side, designing gameplay and building your world. But before we can dive into making things, let's get familiar with the engine itself. In this lesson, you'll learn how to create and manage projects from the Godot Project Manager, and then we're going to take a quick tour of the editor so that you can see what the panels and tools do that you will use most often. Now, before we jump into the editor, let's look at Godot's Project Explorer. This is where you can manage projects that exist on your machine, create brand new projects, or import existing ones in. Now, projects that you've registered, so to speak, with Project Manager will show up in the middle section. And then when you click on a project, you can choose between a few options. The most common ones being Edit, which will launch the editor, or Run, which will launch the build of your game. There's also an Assets Library section, which has templates and demo projects that are registered with GodotEngine.org. Now, these are a good resource if you want to explore and learn from other types of projects, or even get started a little more quickly. Okay, let's create the first project. Click Create, and then name this project Engine Basics. Leave this drop down to Git, and then click the Create button. So there's a lot going on in this engine, but we will break it down slowly. So first, let's kind of look at the panels. On the left side, we have our scene panel. This is essentially the hierarchy. It will display everything that exists within our scene. Now, down below is the file system. This is everything that the project knows about from an asset standpoint. So when you create a new script, it'll live down in this file system. Any models you import, materials you create, whatever assets that this project needs to know about, you'll be able to have access to in the file system section. Next is the middle panel. At the top are 5 different tabs. These are effectively different views that will change this middle section out. So right now we're viewing the 3D view. If we click on 2D, we'll see a 2D representation of the world, which we could even drop. You can see it actually made a scene here. We can drop and essentially edit any 2D elements. So if you're making a 2D game, you're going to work primarily in this screen. If you're making a user interface, you'll view it from this view. Okay, so the third tab is script, which you're actually really not going to be using because we're going to be writing C# inside of Visual Studio Code. The fourth tab is game, and if you happen to play the game and not have it pop up in a separate window, which is an option, then it'll play on this tab. And then the last option is the asset library. This is just like what we saw in the project manager, except it's pulling in different content. So instead of templates and demos, you're seeing a whole lot of different things that are kind of meant to help you speed up your workflow. Now coming back, if we take a look at the right side of the screen, there's the inspector. This is something that you're going to interact with pretty frequently to change the different properties of the nodes. And then next to the inspector is the nodes tab. This is where the signals live, which are events that nodes can send and listen to. These are going to be covered more in depth in the interactions lesson that we'll do later. Now down at the bottom, there's several tabs, but the two most important ones are the output, which is going to show logs, print statements, warnings, and other editor messages that you're going to look at pretty frequently. And then a debugger, which shows information about errors and a lot of profiling stuff that's really helpful for tracking down issues in your project. Now, both of these are going to be covered a little more in depth in the debugging lesson. Getting comfortable with the editor is the first step to feeling at home in Godot. But don't worry if you don't remember every panel right away. As we start building, you're going to naturally come back to these things again and again. In the next lesson, we'll start working with Godot's core building blocks, nodes and scenes. And that's where you're going to start to see how these tools fit together to form an actual game. In Godot, everything you make is built from scenes and nodes. Now, a scene is like a container, and nodes are the individual parts inside of it that each do a single job. A mesh for visuals, light for illumination, or a collider for physics. And you put them together, and you have the building blocks of your game. So for example, imagine a workbench that the player can interact with. One node would handle the mesh so it's visible, and then another would detect when the player walks into range, and then one more would stop the player from walking right through it. Now each node does its own simple task, but you put them together and they're formulating the complete object. So in this lesson, you'll create your first level scene, and then add a ground and set up the player character with a camera, and then of course, save it all in a way that's ready for scripting. Let's jump in and make the first scene, which is the level that we're going to build up throughout this series. So to do that, we can click on 3D Scene, which is going to create a new scene that's effectively a container that has a top level node 3D. Now, what we can do is rename this. We'll call it level 01. And then also, let's just get saving out of the way. So Control S or scene save, and we'll call it level 01. That way we can see our progress as we go. Now we're going to add a child node to the scene that's going to represent the ground. This node is going to have what's known as a static body 3D, or rather that's the type that it's going to be, which is used for objects that don't move, but still need to participate in collisions, like walls, floors, terrain, things like that. So to do that, you can right-click and go to Add Child Node. And this is going to bring up a rather lengthy list within the Node Explorer. And this is effectively a big library of all the different kinds of nodes that you can use for different purposes. Now, if you search for static, you're going to find the static body 3D. And this node actually inherits from several other nodes. You can see here, physics body 3D, collision object 3D, and then node 3D. And that just basically means that it's built on top of them and then inherits their functionality for free. Now, every node has a description, which is this box down below.
and it's pulled in automatically from the documentation. So you can click on any of the links here to get more details on what the node does. You can also tell that there is the hierarchy of inherited nodes too. So you can dive into what, say, collision object 3D does. Now we're going to add this by hitting the create button and then go ahead and rename this to ground. Now you can see here, there is a warning. And what you'll find as you're working with nodes in Godot is that in some cases, they expect something from you in order to function, or something in the scene in order to function. So in this case, the static body 3D node is expecting that there's a collision shape node underneath it. Sometimes they'll flag that they expect a property to be set in the inspector. Now, before we resolve the configuration warning, let's actually add the ground so we can see what it looks like. So once again, right click and go to add child node. But in this case, let's add a mesh instance 3D. And what this is going to do is this is going to let us visualize what the ground looks like. So in the inspector under mesh, click the drop down and choose box mesh. And then to set the right sizing of this, you can click on the box here, and that's going to unfold several more properties. And let's set the size for this. So we're going to go 10, 0.5, and 10. And that's going to let us have a ground that the player can actually walk on. Now, that obviously didn't fix the warning, so we can go ahead and take care of that now by adding a collision shape 3D. So if you hit create, now you can see the warning on the top one is gone, but there's now a warning on the collision shape 3D. And this is basically saying that it doesn't know what shape it should take in order to detect for collisions. So under the property, you can set the shape by clicking the drop down, and then we'll pick box shape 3D. And if we zoom in kind of close, you can see there's this blue kind of bounding box right here. That is the properties that the box is set to for the collision shape 3D, which obviously isn't quite correct because we want that to match what our ground looks like. So once again, you can click this box and it's going to expand properties under that shape, and then we can change these properties to match what we just had. Oops, yeah, no, that's right. What we just had for the mesh instance. And it looks like, I think I might have gone, I went 0.25. I was thinking 0.5 and my brain went 0.25 because that makes loads more sense. Anyway, so we'll fix that. So now they match and the ground is ready to go with a collider. So I'm going to hit save again. And then one more thing to talk about before we jump into the next part is the inherited nodes. So I have the static body 3D selected. And if we come over to the inspector, you can kind of see there's these headers right here. These headers represent properties that are exposed through each one of the nodes that this static body 3D is inheriting from. And all of the nodes are going to inherit from node 3D, or I should say all of the nodes that we're going to work with in this project are going to, not all actually do. And with that, though, comes the transform property. And within this property is where you can set position, rotation, and scale, among obviously a few other things. So position is going to set where this node lives in world space. So if you grab any one of these arrows and drag, you'll see the position changing in value. And then the same thing for kind of these circle ones. These are going to allow you to tweak the rotation. And then if you want to interact with the scale, actually any of these are up here, but if you want to interact with the scale, you can turn on scale mode, and then this will turn into a box and you can drag. Or you can just set these properties directly in the inspector. Oops, not 0 though. And we are actually out because it's trying to keep them uniform. So we'll turn off uniform. There we go. Uniform's actually normally pretty good to have. Okay, now that we have the ground created, let's get the player and the camera set up so that we can actually see what's going on in our scene. Now to do that, we're going to make a separate scene to house them. So go to Scene, new scene. And then again, it's going to be 3D, so go ahead and pick that. And then rename this top node to player. Now, what's really cool is sometimes you can add the wrong node to your scene. And changing it out is incredibly easy. So for player, we actually don't want a node 3D. We want a character body. So you can right click and go to change type and then type character body 3D. And you can see it here. Now, character body 3D is a really cool node type that allows you to more easily manipulate characters through scripts. It handles a lot of checks that you would kind of routinely do every time you're making an interactable character. So hit change, and you'll see here two things happen. First is the icon shifts, and then the second is that there's a warning. If you hover over, this warning is going to be effectively the same one that we just saw on the static body, which it's saying it doesn't know how to handle physics collisions because it has no shape tied to it. So just like the ground, we'll take care of that, but we're going to do it in a minute. So right click, and once again, we're going to add a mesh instance 3D, which is going to be the visual representation of the player. And we'll call this body. And then come over into the inspector, and instead of box, pick capsule mesh. Actually going to change this to move. So now we have a body for the player, but it's kind of hard to tell what the forward direction is. And so a lot of people will kind of handle this a little bit differently. I've seen some people add kind of a cute little glasses in front of the face. For whatever reason, I just like to add an arm that sticks out of the middle of the body. So that's what we're going to do. So add another mesh instance 3D, and then set that to forward direction for the name. Pick box mesh, and then go ahead and click on this, and let's set the properties. I think let's do 0.25 for the X and the Y, and then 1 for the length. And you can click this to hide it away. And on the transform, let's set the position to be maybe -0.5 to stick partway out. And there we go. Now we have the arm sticking out the forward direction. And on that note, it's probably very important to take a pause and talk a little bit about Godot's coordinate system. So depending on if you're familiar with maybe 3D modeling or different engines, a lot of times they'll use kind of different coordinate systems. In Godot, -z is forward. And you can kind of see, for illustration, where we're facing. So this right here is our -z, which is kind of where the arm is facing. +z, +y, -y being down, +x, which would be kind of over on this side, and then -x. Okay, so now that we've partially created the player, let's save it. So hit Control S and then enter. And let's actually solve the collision problem. So go ahead and add child node. And then once again, we're going to add a collision shape. And then for the shape, instead, this time it's capsule. You can see once again that blue bounding area pop up on the collider. And then the error is now gone. So we're good because we didn't change the size of the capsule for the player's mesh. Everything kind of lined up without having to set the properties. Okay, so now that we have the player set up, let's get the camera added in. And the style of camera for this project, or really this series, is going to be a third-person camera that follows the player around. Again, the nice thing about Godot is there's a specific node called the Spring Arm 3D, which is going to help make this a lot easier. So to start, let's actually add a pivot point, and we just need a regular node. And then this can be renamed to camera pivot. And under the node 3D transform, let's move the y-axis up to about 1.8. That's just going to sit above the player. Okay, so what this is doing is it's kind of setting the height of where the camera is going to be at, and then it's going to also act as a bit of a focal point for adding rotation on the camera. Now, as a child of the pivot, let's add the Spring Arm 3D. And this node is super cool. It acts as a mounting point for the camera. So it creates basically a flexible camera arm that will automatically handle obstacles by maintaining kind of the proper distance from the player. So let's say you have the camera, maybe it's 3-4 meters behind the player. And as the player walks to a wall, instead of the camera being behind the wall, it'll actually move in on the player automatically so that the player's kind of always still in proper framing. Now, the only property that we need to set is the spring length. So before I change this value, if you look kind of closely, there's a light blue line that's kind of coming off of the pivot. If I change spring length to 3, that blue line gets extended. The spring length defines the maximum distance that the camera can be from the parent. So when everything's fantastic, it'll be 3 meters away. Now, the last thing that we're missing is the actual camera. So let's add a camera 3D. And you can see that gets added and it's kind of right at that pivot point rather than where we want it to be, which is the 3 meters away. When you go to run your game, this will move the camera appropriately. Now, the only thing that we do want to change with the camera is the rotation. I want this to be at a -20 so that the camera is kind of back here and then looking down at the player. All right, so again, a Control S to save. And let's come into our scene. Now, we can take the player and drop the player as a child of level 01. You can see it's come into the scene. Now, if we pull player up so that, oops, they're on the ground. It's snapping on for some reason there. You can see the player kind of sitting on the ground. And then a really handy way to tell when you've got a nested scene is it'll have this icon here. And if we click the icon, it'll actually open up that nested scene in a tab so that you can edit it. Let's duplicate the player and move it to the second one and just take a look at some of the power of having a reusable scene. So if I come over to the player and let's say for some reason we really want the y-axis to be 2, so it's elongated, and hit Control S. If I come over, both of the players, because they're kind of pointed towards that same reusable scene instance, have now taken on that new property because we changed it in our primary scene. Now let's reset this back to 1. Save it. And we can come back. We can actually get rid of the second player, so we don't need it. It's a 1-player game. And now that we've got the camera in, let's go ahead and hit play. Now, this error happens the first time you go to run your scene on a new project. And it's basically just saying you haven't defined what your starting scene is for a project. And it can be done in project settings. So if you ever set your starting scene to one scene, you're like, that's not the one I actually want, you just hop into project settings and change it. But what's nice is you can also from here just say, hey, select the current scene, and then that'll go and set that in your project settings. So it won't prompt you again. Okay, so you can kind of see the player's head right here and the ground, but it's really dark, and that's because there's no lighting in the scene. So let's go ahead and add that. Under level 01, add child node and type light, and we can add the directional light 3D. So go ahead and hit create. And if we pull back, if you pull this up, one, you can see 2 things happen. I pulled it up and the lighting didn't shift. And that's because it's kind of just like general directional lighting, hence the name. And you can see with these arrows that it's pointing on the -Z. So if we pull this up and over, just because that's what I like to do with my lights, and then turn this so you've got rotation, as you drag it, you can kind of see the light shifting depending on where the arrow is at. So like this could also be something really good for simulating day-night cycles. Now, lighting is a highly complex subject that definitely deserves its own video. But what I'll leave you with is under the properties, there's a couple that you kind of want to play around with at a min bar. And one of those is the color, right? So let's say we're simulating the sun. Well, we'll probably want, for example, a light kind of yellow. This is very dark, but a light yellow kind of emittance. So I really encourage you to play around with these settings and see what they do. And on that note, if you hover over any of these, you will get nice documentation properties. Okay, so now that this light is in the scene, let's take a look and see if we can see anything.
For your challenge, create a new reusable scene, something like an obstacle that the player can't walk through. Drop it into your level scene and then see what happens. Try playing around with the different material settings on the mesh instance as well to see how those affect the rendering of your obstacle. And then in the next lesson, you're going to bring your player to life by learning the basics of scripting and then input handling to make it move. Now it's time to make the player move with code. Code will bring your game to life by giving nodes behavior, telling them how to act, how to respond to input, and how to interact with each other. In this lesson, you're going to make the player respond to keyboard input. And to do this, we'll talk about some of the most important built-in methods that Godot calls on your scripts. These are the ones that you'll use again and again to initialize things, update gameplay, and handle input. And then, of course, also to interact with physics. This lesson builds on the player scene that you just created in the last lesson. But if you skipped that, it's okay. There's the starter and final projects that are on the GitHub repository that you can download or clone to follow along.
Okay, so before we jump into any code, we're going to set up the input map for the project. And you can do that by going to Project, Project Settings, and picking the Input Map tab. This is where you define named actions like jump, fire, move forward. And each action can have one or more events that are bound to it. These are things like keys, mouse buttons, gamepad inputs, and even touch. Now the power here is that you set it up once, and then you can check for that action in code no matter what control type the player is using. So this makes your system incredibly flexible. Now for the player movement, we're going to set up 4 controls. Move forward, move backward, move left, and move right. And then before we assign the events, I want to point out this property that's configurable called a dead zone. Dead zone matters for analog inputs like joysticks or triggers, where the stick might not rest perfectly at 0, which can mess up your vector checks. Now the dead zone defines how much you can move before Godot considers it a real input. So tiny jitters are ignored, but deliberate movements are going to register. Now to add an event, click the plus button, and then it's listening for input, so we can just type W. Do it again and type S. Oops, I always do enter. Left and right. Now that's it. You can hit close, save the project, and now let's add a new script and see something happen. And to do that, I already have a scripts folder here. You can just right click, go to create. If you don't have a script folder and you want it, go to folder. In my case, I'm going to do script. And then under language, it usually defaults to GDScript, so just make sure you're set to C#. And then for its inheriting, we're going to do Node 3D. And then name this player. And then we can open that up. Now, Godot has several methods that come out of the box that you can interact with. And we're going to talk about all of these in depth in a moment. But for now, to see something happen, override the method called ready. And then remove this line. And to print something to the console, it's gd.print. Oops. And then save it. Now, going back to Godot, if you were to run the game right now, nothing would happen. That's because the script needs to live on something that's in the scene hierarchy. So if we go to Player and open it up in the editor, we can drag and drop this script into the script section of the inspector for the player. And sometimes you're going to see this error. This inspector might be out of date. This has to do with how Godot is able to build .NET projects. Now, you can resolve this one of two ways. You can either click the build or run. In our case, we'll run it. And then looking at the console, we can see hello world.
In Godot, there are several methods that the engine will call automatically at specific moments in a node's life. These events act like hooks into the engine's lifecycle, frame loop, physics, and input systems. You can override these methods on your scripts to run custom code. Now let's look at a few of the most common ones that you're going to see. Let's start with lifecycle methods. These are all about when a node enters and exits a scene. As a quick refresher, in Godot, every scene is made up of a hierarchy of nodes that are organized into parent-child relationships. This is often called the scene tree. Now, Godot's lifecycle starts with two setup methods. Enter tree is called when the node joins the tree, but the children might not be ready yet. And then ready runs once everything is in place, so it's a safe spot to grab any children or set references. Then the lifecycle ends with exit tree, which fires right before the node leaves, which is perfect for cleanup. Next are input events, which flow through a pipeline. Once any stage consumes an event, it will stop and it's not going to continue any further. Input is called first. This runs for every kind of input, keyboard, mouse, touch, or controller. And if you don't handle the event here, it gets passed to UI controls. Things like buttons or text boxes. If the UI still doesn't use it, Godot calls one of two unhandled methods. The first is unhandled key input, which only cares about leftover keyboard events. It won't see mouse clicks or gamepad input, but it is handy and slightly more performant if you know you're specifically looking for a keyboard event. Unhandled input is the catch-all. It sees any event that has survived the pipeline to this point: keyboard, mouse, touch, or even controllers. And this is actually where most gameplay input tends to live. So the rule of thumb is, use input if you need first dibs before the UI. Unhandled key input if you only care about the keyboard. And unhandled input if you want to safely grab everything else once the UI is done. Now the last group are frame update methods. Both take a delta time step to keep logic smooth across frame rates. Process runs every rendered frame, and this is really good for visuals, timers, or UI. Physics process runs at a fixed rate, synced with physics, so use it for your movement and your collisions.
Okay, so let's actually make the player move. We don't really need ready, so we'll delete that. And then rather than having you watch me type, I will just paste in the code and we'll walk through this. So first, node 3D is not the right node to inherit from. This should have been character body 3D because that gives us access to things that the character body 3D does. Okay, now let's take a look at what's going on. At the top, we're storing an input direction as a vector 2. This will hold the raw input values for movement. And next, the method unhandled key input is being used because we want to capture keyboard input events that the UI hasn't already consumed. Inside, we'll call input.getVector, which is a helper that combines 4 actions. In this case, move right, move left, backward, and forward into a clean direction vector. Next is handle movement, where we check if input direction is 0, and if it is, we will clear the velocity to prevent the player from continuing to move. Otherwise, we will build a 3D movement vector from the 2D input, apply a move speed, and assign it to velocity. Finally, in physics process, we call handle movement, and then move and slide. Both velocity and move and slide come from character body 3D. And this is what makes the movement system velocity-based. Instead of directly changing the position, we tell the body how fast it should move along with the direction, and then Godot's physics engine takes care of sliding, collisions, and interaction with the world. Now let's jump back into Godot and run our game to see the character move. And there we have it. Front, forward, left, and right. Okay, let's add the ability to rotate the player, which means we're going to need a few more variables, which also means that this is a good time to look at the export attribute. In Godot, you can display your script variables directly in the inspector by marking them with export. To keep things organized, you can also use export group. So for example, here I've made a movement group, and under it I have 2 exported floats for base movement speed and rotation speed. And since they're marked as exported, we can adjust them in the inspector during runtime. I've also added another group called references, which is how I like to organize node references that I intend to assign in the inspector. Okay, so real quick, if we pop back into the editor to see our new export properties, we can see a warning message that the inspector is out of date. So since we're not ready to run, we can just hit the build button and that'll recompile our scripts. And now we can see here things like base movement speed, which we could change to 10, technically at runtime, and our rotation speed. And everything is organized into our headers. Now let's add in handle rotation. Now I think what we could actually do to clean this code up is, now that I'm reading it, we can fix this. So instead of storing the input direction, we should store the move direction. This would be a vector 3. And then set that here. There we go. And then now this is if move direction is equal to vector 3.0, and then this is move direction. That should be a lot cleaner. Yeah. Same thing here. So move direction is vector 3.0, and then we can drop that. And then it's move direction and move direction. Okay, that's a little bit cleaner. Okay, that's definitely one of those moments where you just stare at your code for too long. Now let's take a look at what handle rotation is doing. So first thing is we're just making sure we have references and that they're actually moving. And then I think the more interesting stuff is target angle and smooth angle. So target angle is calculating, well, the target angle that the player should face based off of the movement direction. So the idea is that the player will rotate the direction that they're moving. And then smooth angle is basically making it so that we will smoothly interpolate from the current rotation to the target rotation, and that's using lerp angle. So what that'll do is prevent snapping from happening. It'll make it look a lot better. So then rotation is applying the smooth rotation only to the y-axis, and we're preserving whatever its rotation is for x and z since we don't want to impact those. Now the last thing is we want to handle rotation. Okay, that was definitely an unplanned code shift, so fingers crossed that works okay. Let's play our game and see. Backwards, forwards, left, and right. But there is no rotating. Let's have a look. We did not set the player model. That helps. So if we come over here, we can see base movement speed is actually too high. So we'll drop that back down to 5. Rotation's at 6, but we don't have the player model, which would be the visual. So if we assign that, now we can see the player rotating.
For your challenge, try adding something to your scene that can be activated with a button push. For example, create a spinning obstacle, just maybe a simple pillar or a block that moves from one side of the room to the other when you push the Y button. Drop it into your level and then see how it changes the feel of things when you run around it. And in the next lesson, we're going to look at debugging, how to find and fix mistakes to make sure that everything works the way you expect. Now, one of the things I'm doing these days is teaching a group of kindergarteners to code robots. And the biggest concept that we're continuously working on isn't loops or variables, though those are coming up. It's accepting that bugs are just part of programming. And when something doesn't work, the real skill is knowing how to use your tools to easily track the problem down. In game development, debugging is not just about understanding your code, but it's also about making the invisible parts of your game visible so you can track down what's really happening. And in games, there's a lot happening. Scripts are firing, physics is updating, input events are coming through the pipeline, a UI could be reacting, and more. So in this lesson, we're going to look at Godot's built-in tools for spotting issues like error messages, print statements, and collision debugging. Then we're going to move into Visual Studio Code's debugger to look at how you can use things like conditional breakpoints and more to inspect what's really happening.
To start, let's look at how you can view inspector values while the game is running. So if we enable this game, you can see now there are two tabs, remote and local. Local is basically what you just saw in edit mode. Remote, on the other hand, is actually what's new. It's representing the live scene tree, the actual nodes that exist right now while the game is running. So if you instantiated a new node, you wouldn't see that in local, but you would see that in remote. To view inspector values as they're changing, you can click on a node. And then on the right-hand side, if we scroll down to position, which is what's going to change, and we move the character around, you can see the X and the Z values updating. Now that's one handy tool, but another one is being able to print messages to the output and the debugger windows. So let's do that now. To do that, we're going to add a node 3D, and we'll call this debugger, and then add a new debugger script. Make sure it's set to language C#. I'm going to set this to my scripting folder and create it. So I'm going to add in a new method. And there are three ways in Godot to print messages. The first is print, which is just informational, so it'll show up in the output. The second is pushing a warning, which will show up as yellow and in the debugger. And push error is going to show up in red and also in the debugger. Switch over to Godot. We can once again push play. And down at the bottom, we see this is information, the first message. If we go to the debugger, we can see this is a warning and this is an error. You can actually expand these. We're going to go into looking at stack traces more in a moment. But some bugs are not about logic. They're about things that you can't see. And Godot provides built-in runtime visual debugging tools that let you see invisible game elements like collision shapes, navigation paths, and physics bodies. These aids help you understand what's happening beyond what you can normally see, which honestly happens quite often. So there are four options. You go under debug. There's collision shapes, which is what we're actually going to look at now, and this is going to show the actual collision boundaries around physics bodies or area nodes. There are visible paths, visible navigation, and avoidance, and these three are related to navigation and AI, which we don't currently have in this project, so we're not going to dive into. But before I turn on visible collision shapes, let's look one more time at what our game looks like. Player just looks like a player. Now, if we turn on visible collision shapes, and then come back to play, you can see there's a blue boundary box. This is actually tied, if we go back to our 3D scene, actually our player specifically, and we look at the collision shape 3D, that's what you're viewing just now when the game is running live. Code logic is also a large culprit of issues. And while Godot has the debugger tab, which we saw with our messages, I prefer to do this stuff in the IDE. The first thing that we're going to talk about are breakpoints. And these pause your game at a specific line so that you can see what's happening in the moment. So before we put a breakpoint down, let's add a variable print message, and then we're going to change this variable to 3 at the end. And then let's put a breakpoint right here on the first print statement. And we can run our game directly from Visual Studio Code by going to the Run and Debug tab and pushing the play button. Okay, so we can see the breakpoint got hit. And before we explore that, there's also a series of controls that got displayed here at the top. First two are pretty obvious: stop and restart. These 4 are what's, in my opinion, are more interesting. So the first one is continue, which you can use F5 to do. And this will run the game until the next breakpoint gets hit or the game finishes executing for some reason. Step over executes the current line without stepping into any of the functions it calls. And you can use F10 for this. Step into, which can also be used with F11, executes the current line and then moves inside any function or method that's being called. And then Shift F11 is step out. This finishes running the current function and then returns to the line that called it. So if you take a look on the left side of the screen, there are 3 sections. Variables shows everything that is currently in scope. So for example, we can see print message, which equals 1 right now in that variables tab. The watch lets you monitor for expressions. So for example, let's do print message equals 3. So we're checking to see if that's 3. Right now it's not, but if we use F10, we can move down. Now we're on that line right after, we can see that turn to true. And then the call stack might be one of my favorite sections. This shows the chain of functions that led to the current line of code being executed. So this lets you trace how you got to this point, and a lot of times the issue is actually further down the stack. Now, at the bottom here is the debug console. And this is where you can run code live. So for example, we could do print message. Oh, I don't have count. Print message. And we'll say 3. We can say print message is equal to 1. False. 3. True. I use this all the time. All right. Now this is great for the basics, but conditional breakpoints are something that I find a lot of people don't know about, and they're insanely powerful and incredibly handy when you are writing game logic. So let's go ahead and hit stop. We'll clear this breakpoint out. Now, one of the things that happens very often is you're calling something every single frame. And having a breakpoint every single frame is incredibly noisy, and frankly, you're probably not going to figure out whatever it is that you're trying to figure out if you just have that breakpoint set without a condition. So let's show this in action. We're going to move this variable up here. I'll make this a private, and we'll get rid of this. Now let's do print message plus, and we're going to go gd.print. Okay, so process is going to execute every single frame, which means this is going to be very, very noisy. We'll hit play. You can see it down here. Okay, so conditional breakpoints can make this a lot more powerful. So let's say we add a breakpoint. You want to do edit breakpoint to get to conditional. And there are 4 options here. So the first one is expression. You can enter an expression here, and then that breakpoint will trigger. So we'll say, for example, print message equals 5. And then we'll run that. We can see we hit 5, as you can tell down here, and now we've paused. But what if we want to print a log without having to do gd print every time? So that's another thing you can do here. So if we right click and do edit breakpoint, and also come down to log message, and we can say something like value, and then now we're not going to see every single one, but we should see this on the 5th. Value 5. So we'll remove this breakpoint. Let's actually add gd.print back just so that you can see kind of what's happening here. Print message. And we're going to do edit breakpoint, We'll do hit count and we'll say, let's stop on the 20th. So we'll play. And you can see it's been hit 20 times. Now we're breaking. Okay, so let's do the last one, which is wait for breakpoint. And to do that, we're going to remove this and we're going to refactor just a little bit here. So we're going to say if print message is equal to 10, then only at that point do we want to call print messages. And we'll put a breakpoint on print messages, just a normal one. And then we're going to put a conditional breakpoint that only triggers after another breakpoint has happened. And we'll pick scripting line 22, which we can see is this one, and hit OK. So basically, once we hit print message of 10, then this will hit. And then only after that will this one trigger every single frame. So in this example, it's still quite noisy, but I think it'll be a good illustration. So let's push play. Okay, we can see that first breakpoint was hit. I'm going to hit F5, which is continue until the next. And now we can see that we're hitting this. And if I hit F5 again, we'll see it get hit every single frame.
All right, before we wrap up, here's the takeaway. Debugging in games is about peeling back the layers until you see where things break down. And sometimes it's as simple as a typo, but often it's more about timing, input, or physics behaving differently than you expected. So for your challenge, I want you to play around with conditional breakpoints. It's very easy to forget that these exist, and they're insanely helpful for pausing the game at the right time during frame updates. In the next lesson, we're going to switch from fixing problems to testing ideas by exploring how to prototype environments. Prototyping is about building rough but playable versions of your game to test if your ideas actually work. You can think of this as sketching before painting. You want to know whether or not your composition works before you put a ton of investment in. When prototyping, you might be focused on gameplay such as movement or combat, or in the case of what we're going to learn today, the scene layout. In this lesson, we're going to use constructive solid geometry, also known as CSG nodes, to build a room. CSG nodes will let you create complex geometry directly in the engine. Let's get started.
In the GitHub repository for this series, there is a prototyping section that has a starter project. You can download that project to follow along, and if you do, you're going to see a ground and a player that has the capability to move around the level. Now we're going to build up the environment around that player so that it's got walls and a door. And to do that, to start, we're going to go to Environment, right-click, and choose Add Child Node. And under this, we'll go CSG, do a quick search. You can see many primitives that are listed here. We're going to go with Box 3D since walls are, well, square, like a box, and then hit Create. Now, if I bring the camera around, you can grab this green arrow, which is the y-axis, and pull it up, move it around. It's not very precise, which I find is not great for prototyping. So instead, what you can do is use snapping, which aligns it to a defined increment. You can enable that one of two ways. The first is by holding the control button down while you grab. And you can see it's jumping around pretty high. I'll talk about how we can fix that in a moment. But the other way, if you don't want to hold the control button down, is to come up over here and choose Use Snap. Now, if you do have Use Snap on, when you go to hold the control button down, it'll inverse. So the control button will then represent moving around without snapping. I'm pre-programmed to just hold the control button down, so I'm not going to enable this, but it's there. Now, to change the increment that the snapping is moving, you can come over to this transform and choose Configure Snap. And as I said, it defaults to 1 meter. I personally like about 1/4 meter. I find that that's pretty good. So I'm going to change that and hit OK. Now what we can do is set up the size of our box, and that can be done over on the inspector by setting the X, Y, and Z values. So for our first wall, we're going to go 10, 4.5, and 0.25 for the width. And then I'm holding control down. I'm going to push this wall back till it's in line. And then I'm going to rename this by double clicking in the hierarchy and putting wall. Now, I'm just going to Control D to duplicate, hold down Control again, and then align this here. And it actually looks like they're going through the floor a bit. Oh, they're on the edge. We can still grab both and then bring them up if we want, just a little. There we go, we'll bring them in line. Okay, so I'm gonna pick wall 2, I'm gonna duplicate, bring that into the middle, and then we're gonna flip the wall. So to do this, we're gonna go 0.25 on the X and then set 6.5 on the Z. And then I'm gonna push this back and bring it center. And then one more, Control D, grab this red arrow, which represents the X-axis, and line it up. Now we have a player, there we go, in the room. So if we push play, and then move the player around, we're going to see they go right through that wall, which obviously is not what you want to have happen when you have some walls. So the reason that this happens is because we did not enable collision detection. And that's an option within the inspector under the CSG Shape 3D section. There's Use Collision. And all you have to do is turn that on. And then that'll show 2 more areas, Collision Layer and Collision Mask. And we're going to dive a little more deeper into collisions in the next section. So for now, just leave these alone so they're both set to 1. Only one wall has that, so I'm going to select wall 2 through 4, and I'm going to turn that on. And then again, I'm going to leave it alone. And I'm going to come back over and push play. And now we hit the wall. Perfect. So another really useful property on a CSG node is the operations. And that, again, is located under the CSG Shape 3D section within the inspector. There are 3 options that you can choose from. The first is union, which is how you add shapes together. The second is intersection, which keeps only the overlapping areas. And then the third is subtraction, which is how you can cut holes in another object. You can set these operations directly on the CSG node, which is what we're looking at right now, or you can use something called a CSG Combiner 3D. We'll talk about the CSG Combiner 3D in a moment. Let's just look at how we would cause 2 objects to perform an operation on the nodes directly. So I'm going to come back over to Wall, and I'm going to right-click on that and go to Add Child Node. And then I'm going to pick another box. You can see this box starts right on the child. I'm going to pull it back a bit here. Now, this box, which actually we're going to name to be door, oops, caps lock is on, door hole. Oh my goodness, hole. And then change its operation to be subtraction. And you'll see it changed into a yellow box. Now this represents that it's going to subtract from something. Now, if we click off, the box is invisible. We don't really see any changes in our wall. But if we take this box and pull it in, now we can see that it's cut a hole, more like a window. And this is just how far that box is going through. So right now I have it sitting at about halfway through the wall. And if I hit escape to kind of click off of it, you can see there's a partial hole in it. So let's turn this into an actual door, and we're going to set the shape, or the size of the shape to 3, 3.5, and then 5 for the Z, although actually, so we don't really need to do 5, but we'll leave that at 1. And then I'm going to pull that down and then push it through. And it should be pretty in line with the floor. It looks like that's perfect. And then now, if we go into play mode, you can see that the player can go right through that hole. And they still can't go through the wall. So if we try and run into the wall right next to it. So the collision detection is creating a proper setup within the wall to exclude any of that cutout behavior, which is perfect. It's what we want. So as I mentioned, there is one more way to perform operations to create different types of shapes for your prototyping level, and that is using the CSG combiner node. Now what this does is this groups multiple CSG shapes and then performs operations on them as a unit. Now what we're going to do is we are going to combine all of this room together into, this actually represents a kitchen in the overall final project, Flyby Cafe. So I'm going to select everything, right click, and then choose reparent to new node. And then CSG combiner is right here. And I'll pick that. Now, what's really interesting here is if I click on a regular CSG node, the box one, I'll see under CSG shape 3D, there is no collision option anymore. So if I come up to the combiner, that is where it moves to. There's a use collision option under the shape 3D. So we have to enable that, and it'll go through and process it across the objects that have now been combined to enable collision just like we had before, but again, in a slightly more efficient way.
Now you've seen how to use CSG nodes to block out a basic room. Remember, this isn't just about making something polished, it's about quickly testing ideas so you can see what works and what doesn't. It's also important to note that CSG nodes have performance implications and they're not meant for production. So for your challenge, I'd like you to expand the scene. Add a second room and block out some furniture. Make a dining room with some tables and chairs. And don't worry about making it perfect, just focus on getting a feel for the layout and the flow. And then when you're done laying out your scene, walk the player around. Consider how easy is it to navigate. If you put interactable areas on the table or maybe the wall for the door, can they get to it easily? That's the kind of questions that prototyping helps you answer. In the next lesson, we're going to build on this and look at how the player can interact with objects in the environment. Interactions are what make a game world feel alive. It's one thing to move a character around, but it's when the player can affect the environment, be it opening the door, picking up an item, or triggering an event, that the game really starts to feel responsive and engaging. In this lesson, you're going to learn how Godot handles interactions through its signal system. Signals are Godot's way of sending and receiving events, and they let different parts of your game talk to each other without being tightly connected. You'll also see how nodes like Area 3D can be used to detect when the player enters a space so that you can hook into the action like pressing E to collect an object. So let's dive in.
When a player walks up to a door in a game, how does the game know that they're there? Or when they pick up a coin, how does the game know to collect it? It's all about detection or interactions. And in Godot, we use nodes like the Area 3D to sense when something enters a space so that your game world can respond, be it opening doors, triggering sounds, or collecting items. So in this tutorial, we're going to start by creating a new interactive station where the player can collect chicken. And we're going to use the Area 3D node to detect when the player walks into range. So in the scene panel, let's create a new scene, and we're going to make this a 3D one. Right-click on Node 3D, go to Change Type, and look for Area 3D. The Area 3D node acts like an invisible sensor. It doesn't block movement. You would use a static body 3D for that. Instead, it's going to detect when something enters its space. So we can see we have some errors. Don't worry, we're going to take care of that. For now, let's rename this to Chicken Station. And then we'll save it as a prop. To start, let's give the player something to look at. We'll make this a simple cylinder mesh. We'll set this as a cylinder. We'll make the height 1. The top radius we'll leave actually at 0.5 and the bottom at 0.5. Next, let's address this error, which, as you can see, is that we are missing the collision shape 3D. So we'll right-click, add a child node, and look again for collision shape 3D. And the error is once again telling us that it's missing its shape. So we'll make this a cylinder shape. Actually, no, let's make this a box. I like boxes for areas usually. We'll make this, size. Let's go 2 by, not on the Y, 2 by 2. That should be good. So basically, the Area 3D node is going to handle the logic, like detecting when somebody actually enters or exits, which we'll look at shortly. But that collision shape that lives underneath it defines the physical boundaries within the space. So that Area 3D will trigger if something enters the bounds of this collision shape 3D's blue box. Now, let's do a little bit of a refresh on layers and masks. So the easiest way to think about this is that they are radio channels. The layer is what an object broadcasts on, and the mask is where it's listening. So if we change the mask to 2 and turn off 1, it is only going to interact with objects that also live on layer 2. So let's save the station. We're going to come over to our scene and let's add it in. So you can go to props, chicken station. We're going to drag it in. Looks good. And then let's check what layer our player is actually sitting on, which is 1. So let's move the player. Well, we'll leave them on 1 and 2 and say it's broadcasting on both. All right, now let's make this interactive since this is an interactions lesson. Now I have already set up input within this project. So if you look at input map, there's an interact, which is tied to the E button. Okay, now let's add a script. Pop over to the chicken station and we can add a script here, new script. Make sure it's set to C#, and we'll leave it chicken station, but we're not going to put this under props. We're going to put this under scripting, and we can make a new props folder and hit create. So once again, I'm not going to have you watch me write a bunch of code, but let's walk through what there is here. So within ready, there's 2 signals, body entered and body exited. These are built into Godot. Now, Godot will automatically emit them for an Area 3D whenever a physics body, like our player, crosses into or out of the Area 3D space that we defined with that collision 3D box. Now, if you've worked with C# events before, this should feel pretty familiar. In fact, Godot signals are C# events, and you connect them using the plus equals, and you unhook them with minus equals. Now, the difference is that signals are part of Godot's engine itself. They even show up in the editor, which I'll show you in a second, and they can connect across languages. So if you're doing a project that has both C# and GD script, you can use this across both. Okay, everything else should be pretty similar to what we already saw with the scripting lesson. So let's see this in action. And before we do, I realized that I made a mistake, and the player is actually, I changed the mask. I meant to change the layer. Okay, so now our player is broadcasting on layers 1 and 2, and our chicken station is listening for layer 2. All right, let's push play. So we should see a message pop up when the player enters the blue area. You can see it down here. And when we exit, and then if we come up and I push E, you can see that the player has interacted with the station. Perfect. Now, if you're ever curious about what signals there are, you can see a list inside of Godot. So if we go to chicken, again, we're looking at the area 3D, and you click on node, you can see a list of all of the available signals, or I like to call them events. And because area 3D is inheriting from, well, effectively several nodes, you can see that it's actually getting more than just the area 3D signals. So now that our chicken station can detect the player with built-in signals, let's take this a step further. Oftentimes, you're actually going to want other parts of your game, like the UI or the inventory, to actually react when something happens, and usually through a custom signal. So let's make one. Okay, the first thing we're going to do is add a signal. We'll put that at the top. Now in Godot, the signal attribute defines a custom event called chicken collected. Every time the player interacts, the station is going to emit that signal, just like raising a C# event. And by sending along small pieces of data, like the amount collected and, if we wanted, how much was even left, that signal can easily drive, say, a UI update, which may come in handy in the next lesson. Then we're going to add 2 new variables, something to track the total chicken and the remaining chicken. And then inside ready, we'll just set the remaining chicken to whatever the total chicken is. And then the last thing we're going to add is actually replace this method here with an interact method. And basically what this is going to do is when the player pushes E, it is going to emit a signal. And this is how you trigger a signal within Godot. So within C# for events, you would do invoke. Same thing. So we come back over to Godot. Let's just add a new child. Oops. Let's add a new child node. And we'll call it a node 3D. We'll call this Game Manager. And then in Game Manager, let's create a new script. Probably a bad name, but that's okay. And again, we're going to put this in scripting, and we'll just leave that here and create. Okay, so we'll replace the code like usual. And the big thing here is that within ready, we are accessing that chicken collected event and hooking up a method which will print that it succeeded. Okay, we'll refresh the inspector and then assign chicken station. We see the players entered the area, exited, entered, and with Game Manager, the player collected 1 chicken.
Interactions are all about communication. Area 3D nodes handle the detection of an event, while signals let one part of your game announce that something has happened so that another part of your game can respond. For your challenge, let's create a new interactive object, a milk station. Set it up just like the chicken station, but this time the player collects milk. And while milk probably seems like a weird thing to collect, this is part of the recipe that the player will be able to craft in the next lesson. Milk-dipped chicken. Why milk-dipped chicken? Well, that's what you get when you ask a 5-year-old what you should have the player cook in your game. Either way, in the next lesson, we're going to take these ingredients and build a user interface so that the player can craft their first recipe. User interfaces are a critical part of the player's experience. They're how players see what's happening and how they interact with the systems that you choose to expose, whether that's checking health, crafting an item, or navigating a menu. A good UI communicates clearly, it feels consistent, and it helps players focus on the game instead of fighting the controls. The best UIs almost disappear They give players the information they need at the right time and without overwhelming them. In this lesson, we're going to explore how Godot's UI system makes that possible. You'll see how reusable scenes can be combined to build a responsive interface that looks good at any screen resolution. But a static UI is only half the story. So in this final lesson, we're going to bring everything together that you've learned to connect the interface to player actions and populate it with real game data.
Now, this starter project comes with a few new things, so you're going to want to make sure to grab it off the GitHub repo. So first, there are several new sprites that we have included, which we're going to work with as we set up the UI. There's also an oven, which the player can walk up to and interact with, and that's how we're going to end up calling the UI to show up. And then I have made one UI row called ingredient. So that being said, let's make the first part of this project, which is the UI. Go to new scene and then pick user interface. Now you can see here that the type of top level node is different. It's a control node, and control nodes work a little differently from 3D nodes that you've been using. So while 3D nodes exist in world space with X, Y, and Z coordinates, control nodes exist in screen space with only X and Y coordinates. And if we add another node, you'll see, just like before, there are many control nodes that you can choose from. Some are even nested. So container nodes, as an example, are going to help you handle complex layout tasks. And you're going to use a lot of these to slowly build up whatever it is that you're trying to create. So for what we're doing right now, let's start by adding the background, which we're going to use a texture rect for. And actually, before we even do that, we do need to fix the layout here. So right now, this control node is set to the full screen, which sometimes is great, but for our case, we want to set the anchor to be centered. You can see now we have kind of this X in the middle of the screen. Anchors define how a control will reposition itself relative to its parent. So we want this UI to always be center relative to, well, the screen in this case. Now, if we come back over to texture rect, let's call this the background. And actually, we need to set the texture, which, as you can see, is quite big, but that's okay. We're going to fix that. The first thing that we will do is change this to fixed width proportional. And then let's change its layout size. Here, it'll be 338 and then 386. Now you can see the top parent is center screen, but this is actually positioned, it looks like top left, and we want this to also be centered screen. So we'll change the layout mode to anchors and then pick centered, and now everything is where it should be. We'll save this. We'll call it, whoops, workbench. Probably should have called that workbench UI, but that's okay. Now we're going to add a child to this, which is going to be a margin container. Now, margin containers add consistent padding around its child controls. So this is perfect for keeping UI elements from touching the edges of the screen, or in our case, the edges of the background panel, which we don't want to have happen. We will call this bounds margin. And then once again, we're going to do layout, position, anchors. But we're actually going to set this one to be full rect. We want this to just follow the size of its parent. And then under theme overrides, which this section, by the way, will change depending on what you are working with. And in this case, we have margins. So we're going to set the margins here. Let's see, right and left. Let's go 20. And then I'm going to bring the top and the bottom in a little more. It's going to be inconsistent. That'll be okay. I just want it to come down a little. And that's it. Save again. Now I want to add a vertical box container, or VB box container, as a child. Now this one will automatically stack its child controls vertically, one after another, and then it handles spacing for you as well, which is really handy. We'll call this bounds vertical. And then we're going to add one more as a child of that. And this will be our content. So hopefully you can see what I mean in terms of you end up adding a lot of these container nodes to build up towards whatever the look and feel is that you want. So with this content one, we're going to set the layout, container sizing, and on the horizontal, we're going to do shrink center. For the vertical, we're going to leave it fill, but we'll check expand. And then underneath this, we're going to add another, but this is going to be an HBox container. And this is going to be called title row. Now the HBox container does exactly what the vertical box container does, except for now we're going horizontal. And we'll add a little bit more so you can actually see now what's going on. So to start, let's do another texture, rect. And we'll call this actually title icon. And then we'll call this, or we'll set the texture to chicken cooked. And for this, under expand mode, we'll do ignore size. We want to set the size. And then under stretch, we'll say keep aspect. So we don't want it to stretch funny. And then under layout, we'll do custom min size is a 32 by 32. Okay, so now under row, let's add another one. And this is going to be a label. This will be basically our header. We'll call it title label though. And then under this, we'll say cook chicken. So under theme overrides, there's lots of different properties because we're interacting with a label. And in this case, we're going to change the font color. And we'll make this, let's see, what did I want? 8CB7C8. No, I did not have that memorized. And then font size, oops, not that, font size. We're going to make this 25. Hopefully you can kind of tell here, title row, we're going that way. Let's actually move this to be a child of content. And now you can see it's going to stack, as I mentioned, vertically. And it handles all of that positioning for us, which is just so handy. So now that that's done, we're going to add the next thing under there, which is going to be another margin container. And this is actually our divider. It's just going to make it look all nice. And underneath it, we'll add a panel. Actually, let's call this container, divider container, and then we're going to call this divider. So under layout for this, we're going to set this to 3. And then theme overrides here, we want to set the margin. We're going to do the top and the bottom. And this will be 10, just to give a little space between. And then the divider is going to be the actual, I guess, line that separates the two. So with this, we can pick the style box flat. There we go. Well, we're going to set the color here to be 223C57. Be like a light blue. It's actually not quite. There we go. And I did want to set the radius here. We'll do this as a 3, give it a little bit of a rounded edge. There we go. All right, so then we have an ingredient header that we want to add. This will be a label. And then we'll set the text property to requires. We're going to match the font color here. So I'm just going to come over here, copy that so you don't have to watch me type it out again. And where are you? Theme overrides, colors. And then let's set the font size here to 20 pixels, just to be a little bigger. All right, we're almost done with this section. So what we want to do here is add buttons, and we're going to add a container as a child of bounds vertical. And this will be our center container. A center container will make its children center both horizontally and vertically, which is great for kind of spacing out our buttons. And we'll call this buttons And then we'll add a HFOX container because we want these to go horizontally. We'll call it buttons row. And then let's space these out. We'll space them out by 15. This is a good place to pause for a moment and talk about what the buttons are that we're going to add and how we're going to impact the way that they look. So there will be 2 buttons, cook and close. And typically when you have a button, you want to have a different visual representation depending on the state. So you'll have how they look normally, how they look when hovered, and how they look when clicked. Now, instead of using separate images, what we have here is, there we are, is a single image that represents the 3 states that I've just mentioned. This is a pretty common practice. You typically want to pack your sprites into a single sheet because it's a lot more performant than having a bunch of individualized sprites. So I wanted to kind of show you how you could do the individual thing. Now we're going to explore how you can pull a single sprite out of a texture that has multiples. So coming back over to buttons row, let's add a new child node, and oh, it's right there. We're going to add a button. Oops, needs to be there. And we'll name this button cook. And we'll set the text property to cook. And then under layout, there you are. We're going to set the minimum size here to be 75 by 30. All right, so now let's configure the buttons atlas. And this, again, will be under the theme overrides and styles. So you can see there's actually several different ones that you can change. But like I said, we're going to focus on really just 3. We'll do new style box texture. And then under texture, we're going to set this to an atlas texture. And then click that to expand it. And now we'll drop this in here. And then under region, we'll do edit region. And zoom in a bit here. Now you can choose auto slice, and it'll change these blue boxes to be where it thinks the images are. You can manually do this if it gets it wrong. Now we'll pick the first sprite and then hit close. And then coming back to, whoops, and to close that. Coming back to this, let's set the texture margins to 7. Okay, now we repeat that same process for the other states. So hover. And then we set it once again to atlas texture. And then button sprite, the regions, and we'll pick the second one. And then again, the margins set to 7. And we can close that. And then the, oh, pressed. Texture. Then add this. Once again, just drop the image. Edit region. Select that. Texture margin 7777. All right, there we go. Now, instead of doing that for the second button, we can just copy this one. Now it's a child. There we go. And rename this button close. Okay, so this feels like a good place to pause and drop this in to see what we've just built. So if we look for it, make it child of the scene. All right, you can see if you click, nothing happens. But actually, if you do click, there's that border. I don't like that border. So let's get rid of that real fast. So if we come back over to this button, it's going to be, let's see here. That is actually not on pressed. That is focus. And we're going to say new style box empty. I just don't want anything to show up. So the same thing here, we'll go to overrides, styles, focus, and we'll make it an empty box. Save. I think we're still in the scene, right? Yep. Okay, no white box. And before we jump into the code side, let's look at what it is that we're actually going to be creating. And the end goal here is to have you walk through instantiating a UI component dynamically in code and then populating it with information, since this is a very common use case that you're going to encounter. So, as I mentioned before, I created an ingredient row, and where this is going to get instantiated is within the content section. And we're actually going to do 2. So it'll look something like this. And the ingredient is going to shift in terms of the text that you see in the icon, depending on what information that we supply it with. Right now, it's just chicken uncooked and milk, so it'll stay the same on one of them. Okay, let's get rid of these and let's add a new script. We'll call this workbench user interface. And put this again under the scripts folder. Great. Okay, so before we jump in, it's worth noting that Workbench comes with a script. And this script is essentially a mirror of the chicken station in terms of how it works. The player walks up, they press E, and the workbench will emit a signal, which in this case is workbench interaction. And we're going to update the workbench user interface to populate the ingredients, subscribe to that signal, and then handle showing and hiding itself. So if we add the code in here, actually let me zoom in a little bit, make that easier to see. Okay, so up at the top, we have our references. The craft button and close button are just references to those buttons. And then content container is the section that I mentioned earlier we were going to add the ingredient rows to. Workbench is a reference to the workbench so that we can get a subscription to the signal. Now within Ready, 5 things, I guess technically, are happening. The first is it's hiding itself. And that hide and actually show, which is down below, are methods that are available because this is inheriting from control. So the next thing that's happening is it's going to set up the ingredients, which to start, it's loading the scene as a template. Now, technically, we could add this as a reference, but I thought this was a good opportunity to show how you can load resources through code. And the next thing that it's doing is it's looping through the strings, which in this case, we're doing 2 ingredients, milk and chicken, and it's instantiating them. Then it's taking content container and it's adding this as a child to it so that it's in the hierarchy where we need it to be. The last thing that's happening is it's calling setup on the ingredient class, which is another class that's provided on the starter project. This isn't really doing anything fancy. All it's doing is it's setting the name of the ingredient to the string that we pulled out of the array, and it's looking up in the dictionary for the correct texture. So next, for the on workbench interacted, which is triggering when that signal is emitted, we're showing the window. And then when the close button is pressed, we're hiding it. Lastly, when the craft button is pressed, we're just doing a print saying that it's been pressed. And that's it. Okay, so let's pop into Godot, and we need to refresh the inspector so that we can set the variables. And we'll assign these buttons. So close, cook, I guess I started calling that craft at some point. Workbench we're skip because we're going to get that in the scene. But content will be this one. We'll go ahead and save that. And then for other references, we can pull in the oven or workbench. I'm very consistent in names today, apparently. And then hit save, push play, walk up, push E. Oh, let's click cook, close, and that's it.
Before we wrap up, remember, great UIs aren't about showing everything. They're about showing the right things at the right time in the clearest way possible. If players can instantly understand what's happening and what they can do, the UI is doing its job. Build your interfaces from small, reusable pieces, rely on layouts instead of manual placement, and always test them from the player's perspective. For your challenge, take these ideas further by creating a simple inventory. Lay out a grid of slots, Let the player click to select an item and wire it up so details appear when they interact. It doesn't need to be flashy. The goal is to practice turning static layout into something dynamic and responsive.